Good day, everyone, and welcome to week 3 of PMGT1865. This is the project time, cost, and resource course. I'm Dr. Kumaran Murugan, your academic lead. Today's session is on overlapping networks and precedence diagram, which will be built on last week's CPM, the critical path method diagrams, and help you model more realistic project schedule where tasks may not always follow a strict finish to start sequence. Today, I'm going to guide you through the overlapping network models and precedence network diagram concept. Last week, we explored project schedule and in which we spoke about task dependencies. As a project manager, we might come across activities which may not be occurring the usual finish to start or activities that are occurring at the same time. There may be activities which you may come across with time delays and how it affects the precedence or the successes activities, like which activity should start late, how long should the time be, or which activity should start early before the precedence activity. So those kind of how we deal about those activities is what we aim to cover in this section. At the end of the course, you should be able to understand the overlapping and precedence activities and how to manage those. Let's get into the course. Okay. By the end of this session, you will understand overlapping network models, recognize the different types of relationship between activities. You should be able to develop an overlapping network diagram from a WBS and calculate the critical path in more complex and real world networks. And you keep these in mind as we progress. They are your checkpoint for learning today. What you're seeing is the project schedule overview for the class, and we covered in week 1 the introduction. We saw about the project planning in different contexts and project scope, and in week 2 we discussed the project schedule, the work breakdown structure, and how to make critical path. And in week 3 we'll explore more on advanced or complex critical path in which activities can be overlapping through in the overlapping network diagram. Okay, what is overlapping network diagram? So in traditional network diagram, we usually assume activities occur in sequence. But in practice, especially in engineering or construction kind of work, some activities will overlap. An overlap network diagram shows these partial or full overlaps. This let us optimize workflow by running tasks in parallel when possible, balance resources by avoiding bottlenecks, and it improves communication with stakeholders by showing concurrency of activities. And you got to remember, WBS answers what needs to be done. It differentiate activities, what are the activities that needs to be done, whereas a network diagram show how and when these activities are related. So that's a crucial part. So the task dependency is a crucial part in network diagram. Okay, so in network diagram, in overlapping network diagram, there are 4 types of precedence relationships, we call it. So the first one, we call it is finish to start. This is the default mode. Most of the project, I think 100% of the project will have this as a default. So when activity finish, the successor activity starts. So the successor activity starts after the predecessor finishes. Successor activities cannot start until predecessor's activity has finished. Activities are in series. This is the most common relationship in project activities. One example you can think of is like think of finish to start as a painting only after plastering is done. So only when the plastering work is done, you should be able to paint. So that's the finish to start. So the next type is the start to start. The successor starts only after the predecessor starts. Successor's activity cannot finish until predecessor activity is finished. Activities are in parallel. This is next most common relationship. Think about example as laying cable while excavation is underway. So you can still do the laying of cable while the excavation is underway. So it's like start to start. So the third type is to finish. The successor activity finishes only after the predecessor activity finishes. Successor activity cannot finish until the predecessor activity is finished. Activities are in parallel, and this is again the most common. So what are the example that we can think of is testing finishes only after installation finishes. So only after you install a system or a chipboard in an electronic situation, the testing can be done, something like that. So the fourth type and the last type is the start to finish. This is a rare type, start to finish. It is one of the least common, and the successor activity finishes after the predecessor activity starts. This is kind of hard to imagine, and this is, as I said, it's the most rare situation. Successor activity cannot finish until the predecessor activity has started. So how can a successor activity, which is, for example, if it's an activity B, cannot be finished only if activity A is has started. So this is the least most common thing. So I can give you an example. Think of a security at a construction site. So security, there is a 24-hour security requirement. So the predecessor, the activity A of day shift, day security contractor arrives and signs in. Until a day security comes in and signs in, the successor activity of finishing the night duty, night security cannot sign off. So something like that. So only when night security contractor signs off, the day contractor arrives and signs in. That's the concept that we can think of. This pre-decision activity cannot start until the successor activity of night shift security signs off. So this is one example. So why we do start to finish is having a continuous security. We need to have 24-hour security. So the night crew cannot finish until the day crew start. That's pretty much, yes, that's the easiest example we can think of. And okay, so let's go into, we also have lag and a lead. So what is lag and lead? So the delay between predecessor activities and successor activities is called lag. If there is a positive, if, for example, if activity A has to start, has to finish, and then activity B starts 2 days later, that 2 days becomes your lag time. It is the amount of time whereby a successor activity, which is like a activity B, can be delayed with respect to the predecessor activity. We call it positive lag and negative lag. Positive lag equals intentional delay. So you got to wait, for example, if you're pouring contract in construction, you have to wait for 14 days for the contract to cure before you can start carpentry work or even painting or anything. Negative lag, which is also called as lead time, it is about the amount of time whereby a successor activity can be advanced with respect to a predecessor activity. So it's like start earlier than standard sequence flow. So let's see what the formula for lag between activity I and J as shown in the slide. Lag of activities I and J is equal to early start of activity J minus early finish of activity I. That is your lag. In a normal finish to start relationship with no lead time, your lag will be 0. But in very complex schedule, lags can vary between activities. So you might have different days or hours between activities. You may explore few examples of lead from your own WinForm activities. So in the finish to start slide, if you the one you've been seeing now, in this example, we have finish to start with the 14-day lag. If you see between the activity I and activity J, there is a lag time. So you got to leave 14 days for curing time after rendering activity before painting begins. Look how the precedence activity I, 5-day work of rendering wall is being scheduled. Then curing wall happens. The cure render is lag time of 14 days, which is kind of, if you look at the bar chart, it is from 17 to 31, which is your 14 days. And then painting start, and which is to be finished in 4 days. A simple network diagram, which you see below, its early start will be 31 days. Early start time, which is your EST, and ETF is nothing but your early start and early finish time respectively. So how do we calculate that? Early start time, which is your paint walls, equals early finish time of rendering your walls plus your lag time, which is your 31 days. 17 plus 14, 31 days. So this lag ensures quality but impact the schedule flexibility. Let's look at the start to start example. Here, footings can begin 3 days after excavation start. So in a construction world, if you think of footing service, it has to be done after excavation start, right? So this is a start to start. Look at the start to start with a lag of 3 days. So the excavation site start its activity on the day 12 and then it can go up to 15. That is your lag time. After that, your this activity J, which is footings of service core, should be starting. The successor activity cannot be start until preceding activities have started. Usually what this means is some portion of preceding activity must have been completed. As you see, that 3 days has been completed. The pre-completed portion is referred to as lead time. Look at the bar chart. See how some part of excavation activity has started. Following like 3 days later, footing work commences. So how do we calculate the early start time for the footing, which comes from early start time of excavation plus your lag time, which is 12 plus 3 equals 15. So the footing activity will start on 15 day or the day 15. This overlap shortens the project duration but requires very close coordination. Let's look at the other scenario or the other type in finish to finish. The finish of the successor depends on the finish of predecessor, which is kind of a fairly easy example you can see. Look at the topmost picture there. Activity I and activity J finish at the same time with no lag or no lead time. Activity J can also be finished after activity I with some lag time but should not have lead time. It cannot be finished before activity I because of the concept called finish to finish. So one example we can look onto is installing and testing ventilation, which can start early but must finish 4 days after power is supplied. So something like that. So in this case, early finish time of an install and test equals early finish time of power and ventilation plus 4 days, which is your 25 days. Then comes to the last complex phenomena, which is your start to finish, which is a rare phenomena. It refers to successor activity cannot finish until predecessor activity has started. This is one of the least common relationship. And if you see an example here, the finish of lift testing depends on the start of electrical wiring. So you can still start the activity J, which is installing your lift, but you cannot power it up. You cannot give power until all the electrical wires has been done. So once you have the activity J of installing your lift, you cannot test it until the activity of electrical wiring has been implemented. So in this case, the successor activity AI, so I is electrical wiring. This activity cannot be finished until lift installed. So followed by testing. This is the concept of start to finish. It is used in very specific sequence, often in shutdowns or switchover operations. Usually, as I said before, it is rarely seen in any project activities, but you should understand what these four different types of overlapping activities will be. Okay, out of all the four types, there's one more concept called compound link. Sometimes activities have both start to start or finish to finish constraint, which is what we call a compound links. So it is an activity of having both start and finish to finish constraint, which is called compound links. In project scheduling, a compound link, sometimes called a compound dependency or double constraint, it is called the double constraint, is when two activities are connected by more than one logical relationship at the same time. Which means you look at when two activities are connected by more than one logical relationship at the same time. So let's see why it is used. To model overlap and alignment in complex workflows, and to control both start and finish of an activity relative to each other or one another, to handle partial overlaps where just one link type would be enough, would not be enough, sorry. So for example, lining can only start day 4 after stud wall start, which is your start to start, and can only finish 3 days after stud wall finish has been occurred. So managing compound links is a crucial realistic schedule. And what is the key point here? It is the most schedule tools like Primavera allow compound relationship, but usually not in MS project. So in MS project, you don't need a break activities into smaller tasks to model both relationship. Okay, so I think we covered most of the overlapping concept here. So what we understood is the overlapping network model. We have recognized the different types of relationship between activities. We learned how to develop an overlapping network diagram from a WBS. We calculate the critical path in more complex and real world. With these, we conclude this session and thank you for your time. Please feel free to share your question to the academic team. If you have any questions, please email me or Jin or Kerry. Otherwise, have a wonderful night day.